Hello friends, welcome to G-Centric. So in this lecture we will see the problems based on the Thevinin and Nortons. Okay, so before going into that, okay, so this is question number 132. That means we have till now we have solved almost 131 questions. So from now on this will be the numbers that we are going to cover rest of the questions. Before that, before going into this problem, okay, so we have seen that VTH and RTH for the Thevinin theorem. Okay, so this VTH is nothing but terminal voltage, okay, or you can also call it as open circuit voltage. Okay, so this RTH, when you have to calculate the value of RTH, you have to keep the sources, okay, sources inactive. Okay, how do you make this sources inactive? We have already seen, if it is voltage source, it will be short circuited. Okay, if it's current source, it will be open circuit. Okay, so this was that one thing that we have to keep in mind. So while calculating RTH, we have to short circuit the voltage source and we have to open circuit the current source. Okay, so now we will come to this problem 132. Okay, so coming to this 132nd problem, we have to find the current I. So the current I is mentioned here. Okay, through this 1 ohm resistor, we have to find the value of the current. Okay, so using both the theorem, which are the Thevinin and Norton. So now, the first step is, we will go stepwise one by one. Alright, so our step 1 will be, for this is for Thevinin. Okay, for Thevinin we are going to find the first. Okay, step 1 in Thevinin says that, okay, whichever response in whichever branch the response is asked, okay, the response can be either current, voltage or power. Okay, make that branch open circuit, make that branch open. Okay, so what, according to this first step, what will be our circuit? How will it look? So this will be plus and minus 12 volt. So this is 6 ohm. This is 2 amperes. Okay, so this is next 6 ohms, 4 ohm, and here this terminal should be kept open. Okay, and this will be VTH. Okay, so we have seen that VTH is nothing but the terminal voltage or open circuit voltage. So first step in the Thevinin is that we have to open that branch in which the response is asked. Okay, so now this has become our first step. Next, our step 2 is, step 2 says that calculate VTH. Okay, we have to calculate VTH by any method. So with the help of any method that we have learned till now, we have to find this terminal voltage. So how do we find? Now if I see, this is, I'll go by nodal analysis, this is grounded. Okay, so this terminal voltage will occur here, VTH, that is same. Okay, no element is connected. Now here it is 12 volts. Okay, so this we will take it as V. Alright, so once we will calculate V and once for VTH. Okay, so we know how to write the nodal analysis. So from V minus 12 by, this is 6 ohm. Okay, then plus we have V, this is how much? 2 amperes. So then here we do not have anything, we have that side V minus VTH divided by 6 is equal to 2 ampere is the incoming current. So LCM is 6, so you will get V minus 12 plus V minus VTH equal to 12. So this 12, if it goes that side, it will be 24. So this is 2V minus VTH is equal to 24. So this is equation number 1. Next, we will calculate at this node VTH. So VTH minus V divided by 6 plus VTH divided by 4 equal to, is there any incoming current? there is no incoming current at this node, so it will be 0. Okay, so now this LCM is 6 and 4, I think it is 12, yeah, it is 12, LCM is 12 for this one. So 2 VTH minus 2V plus 3 VTH equal to 0. So 2 plus 5 VTH minus 2V equal to 0. Okay, so now through this what we will get, how much, I'll just check with it. Yeah, so this will be equation number 2. So now we have to simultaneously solve this both the equation. I'll rewrite equation here. So this is minus VTH and this is plus 2 volt equal to 24. Okay, so this is 4 times VTH. This and this gets cancelled and you have got 24. So VTH value will be 6 volts. Okay, so now you know what is the VTH. Okay, now once I'll rub this one, I'll write it here, it as VTH is equal to 6 volts. Okay, we will go to step number 3. So step number 3 says that you have to calculate, step 3, calculate RTH. So how do you calculate RTH? That is R equivalent or Thevinin equivalent resistance. You have to open source the current source and short circuit the voltage source. So I'll short circuit this one. This is 6 ohms and here it is open source and then I have 6 ohms. So here it is 4 ohms. Okay, so this is VTH and I have to calculate R Thevinin. So these both are in series, these both are in series, that is 6 plus 6 is 12 and this is in parallel, 12 into 4 by 16. So it is 3 ohms. Okay, so now this up to here step 3 is completed. So we have got R Thevinin also, that is 3 ohms. So our step 4, after calculating this one, what will be our step 4? To draw the circuit diagram of reduced, we have already reduced this into VTH and RTH. So circuit diagram is reduced to Thevinin equivalent. Okay, so now what does it say again? Step 4, what it will say that you have to rejoin the open branch. Rejoin the open branch. So how do you rejoin it? Now we have got VTH. So this is VTH and we have got RTH, and which we have open circuit, the branch that was open was 1 ohm, and we have to calculate the current through this 1 ohm resistor. Okay, so this VTH value is 6 volts and RTH value is 3 ohms. So I is nothing but total voltage in the circuit upon equivalent resistance, that is RTH plus 1. So it is 6 by 3 plus 1, 4. It comes out to be 1.5 amperes. Okay, so this is the Thevenin's equivalent. So there are 4 steps in it. Step 1, we have to open the branch in which we have to calculate the response. Second, we have to calculate the VTH, that is the terminal voltage. And third, we have to calculate the R Thevenin, that is keeping the sources inactive. And the fourth step is whichever branch we had opened, we have to rejoin it and we have to calculate the response, reducing this to VTH and RTH. So this whole part, the left hand side of the circuit is reduced to one voltage source and one equivalent resistance. So now this same problem we will solve with the help of Norton's theorem. Okay. Okay, coming to this, so using the Norton's theorem. So now this will be, most of the steps are same except for the step 2. Okay, so in step 1 in the Thevenin's theorem we used to open this branch, but here we will do short circuit. Okay, we will remove that branch and we will short the branch. So this branch will be reduced to 6 ohms, then we have 2 ampere, then we have 6 ohm, 4 ohms, and we have to short this branch. So which the branch that we shorted and the current that flows over here, we will call it as I short circuit or IN, that is the Norton current. Okay, so this is terminal A and this is terminal B. So we have to find this one, I short circuit current. Okay, so now this was our step 1, we have done that. So our step 2 will be, step 2 is to do source transformation. Okay, we have to reduce it to Norton because we have to reduce to one current source and one RTH or RN. In this case, we will call it as equivalent resistance of the Norton. So source transformation, what we have to do? So we will change this voltage source, okay, and this current source, sorry, this ohm, okay, 6 ohm resistor. So this will come in parallel with 12 volt or the current that we are going to replace the current source with the help of source transformation. Okay, so now I will take this as, so what is I? I will be equal to V by R. So this value will be 12 by 6, that is 2 amperes. Okay, so this will come in parallel 6 ohms, 2 ohm it will be as it is, and here it is 6 ohms, so this is 4 ohms. Okay, so this will be ISC. Okay, so now this 2 ampere and this 2 ampere, they are in same parallelly connected and in the same direction, so we can add it. And what will happen to this branch? Now if you observe carefully here, okay, so this branch, okay, 4 ohm, this is short circuited, right? So now this will be 0 volt. Okay, so when here it is 0 volt, since this branch is short circuited, here also it will be 0 volt. Okay, so this node is also having 0 volt, here also it is 0 volt. So this branch does not have any significance. Okay, so this will be open. Okay, 4 ohm will be having no role in this. Okay, so I can write it as 4 amperes. Now this I can make it open. So this will be 6 ohms and here it is 6 ohms and the current flowing through this is ISC or IN. Okay, so now this is 4 amperes, 6 ohm, 6 ohm, both are same. So the current will be, no need to apply current division rule because both the values are same, current will be divided equally. So we have got ISC is equal to 2 ampere. This can also be written as IN. Okay, so now for the step 3, for calculating RN, it will be same procedure. You have to deactivate both the sources. So short circuit the voltage source and open circuit the current source. Okay, so now step 4, we have got ISC here as 2 amperes. So in the step 4, we have to rejoin the branch. Since it was short circuit, we will add back the, rejoin the resistor. Okay, so now it is reduced here. This was 2 amperes. Okay, ISC current is 2 amperes. Okay, and we had got RN as 3 ohms. Okay, so the RN is equal to 3 ohms. See, this will be in parallel. In Thevinin, it will be in series. Okay, so I will rejoin the resistor 1 ohm. Okay, so now I have to find the current in this one. I can apply current division rule. So current division rule will be current through this 1 ohm resistor will be 3 by 3 plus 1 into 2 amperes. So this will be 3 into 2 by 4, which comes out to be 1.5 ampere. So this is same as the previous Thevenin's theorem. So in whichever method you solve, we will get the same answer. But there are certain things which can be applied only using Norton theorem and some circuits only can be solved using Thevenin's theorem. So now in this process, we will take 3 cases. That is, case 1 we will only solve using the independent source. Second case we will solve the combination of independent and dependent, and the third case we will solve using only dependent sources. Okay, so we'll go to the next problem now. Okay, coming to this 133rd question, so we have to find VAB. Okay, so this VAB is here, that is open voltage. Okay, so basically it is nothing but Thevinin, or we can use Norton, both of them. Alright, so we will first, if you see this, here is, if you convert this current source into voltage source, if you using the source transformation technique, then these two will be in series. Next, if you convert this voltage source into current source, this resistor will come in parallel, so it will be easy to simplify. Okay, so now this simplification how we will do? So this V is nothing but I into R, so I value is 6 into 5, you will get it as 30 volt. So this will be replaced by, see the polarity, plus will be down. Okay, so this will be 30 volts, and okay, I'll redraw here, minus plus 30 volts. Okay, so this will come in series with this resistor. This is 5 ohm, this is 10 ohm, and here we have open branch, that is A and B. Now in this case, this resistor will be as it is 10 ohm. Now this will come in series, series will come into parallel for converting it into current source. So for current source it will be V by R, that is V is 16 by 10. So how much it will be? 1.6 amperes. Okay, so this will be the current. Now I can still further reduce this circuit. Okay, so 10 plus 5, okay, I'll redraw here, plus minus 30 volts, sorry, this is minus plus, so be careful of the polarity. Alright, so this is 10 plus 5 is 15 ohms, here it is A and here it is B. Next this is replaced, okay, I can replace this also in series with the current source. So this will be 10 and 10 both are in parallel, you will get as 5 ohms, and current source is 1.6 amperes. So now this will be VAB. Okay, so now you can apply nodal analysis, right? This will take it as reference node. So here it will be how much? Minus 30. Alright, so here it will be, okay, there is direct, we have got incoming current. Alright, so we will take this as, we can apply nodal analysis, at VAB. Okay. So now before that, so instead of applying directly to the current source, okay, I will again get back it into voltage source, so that still it will be very much easier for me to solve with the help of nodal analysis. So now if I take this as 30 volt, 15 ohms, A and B, I will get this 5 ohm in parallel, and here this will be plus and minus. Okay, so V will be equal to 1.6 into 5, so 630, so 8, so I will get it as 8 volts. Alright, so this will be 8 volts. No, it will not be in 8 volts, since this we have taken it as 10 into 10, 5, since it is coming in series, we will directly convert it into 5 ohms. Here it will be 5 ohms itself. Okay, so sorry, this was in the series, it would come as 10 into 10, 5 ohms. Okay, then using again the source transformation technique, I have written it as 5 ohms. So this circuit will be wrong. Okay, so because it has to be in parallel, then I have to convert it into source voltage. Now you can apply nodal analysis to this problem. So I will take this as reference node, and this is VAB. Okay, now I will rub this top one so that From VAB to 30 volt, we have got VAB plus 30 divided by 15, then plus VAB minus 8 divided by 5 equal to 0, right? So now what will be the LCM of 5 and 15? It is 15. So VAB plus 30 plus 3 VAB minus 24 equal to 0. So 4 VAB equal to 30 minus this will be minus 6. VAB will be equal to minus 6 by 4. It comes out to be 3 by 2, 1.5 volts. Okay. So here that was one mistake, that it will be in parallel with the current source, then you have to apply the source transformation again to get back into series and voltage source. Okay. So this is how we will solve. You will get it in negative. So check the calculation again. It is 4 VAB 6. If it goes that side, it will be minus 6. So you will get the answer in negative. Alright, so this was asked in GATE 2017 electrical branch. Next we will come to this 134th question. We have to find VTH. This was asked in the year 1999. Okay, so they have given AC analysis. This is also on case 1, that is independent sources. Now you have got inductor, capacitor, resistor as well as one more inductor, and here is the VTH open terminal voltage. Alright, so now okay, all are in ohmic values. In AC analysis, first we have to consider if they are in ohmic values or no. So this is all capacitor and inductors are in ohmic value. Now this is VTH. So here also it will be same VTH. Okay. Now if you observe here, it is 100, 0 degree. So from here to here there is no element present in between. So I can take this node as 100, 0 degree volts, right? So now I can apply voltage division rule, right? I want this J4. So this VTH is nothing but same voltage that occurs across the inductor. Okay, they are in parallel, right? There is no branch here also. So whatever VTH is here, it will appear to the inductor. Okay, so now I can apply voltage division rule for this one. So voltage across J4 will be J4 divided by J4 plus 3 into total voltage. Okay. So now this 3 plus 4j I can rationalize. How do I rationalize? 3 minus 4j divided by 3 minus 4j into 100 angle 0 degree. See here it is, they have asked it in J16. No, so you do not need to go to the phasor domain. So see the answers, then start solving the questions. So you have got 4j into 3 minus 4j. So this is into 100 0 degree, 3 square plus 4 square. So 16 plus 9 is 25. So 25 and this gets cancelled by 4. So 4 into 4 is 16j, 3 minus 4j. So in the option it is first one. Okay, so this is the AC analysis. It looks complex but it is not complex. So this was in the case 1. We have solved only about the taking the independent sources. So from the next lecture we will see few more problems based on this. Then we will switch to mixture of dependent as well as independent sources. Okay, thank you.